Come on in, everyone. Feel free to ask me any questions while we're waiting for the other people to come in. No questions? I was just looking back. We had started chapter 7. In fact, let me look at the notes from the previous chapter 7 work. Okay, we had just gotten through work, defining it, defining dot products, that kind of thing. Gotcha. Just want to make sure I was still on the right page as far as what we're actually doing. Anybody have any questions on any homeworks or anything? If you had lab today, which no, none of you have lab today. You guys have lab on Thursday, if I'm not mistaken. Is that correct? Or excuse me, Wednesday?
Thursday.
Thursday. Okay. That's cool. So your
I
exam
have a
will
question.
happen then. Yes, go for it.
When is chapter 8 homework due?
Okay, I just noticed that the changes I made Thursday evidently did not take or something, because it showed chapter 8 was already due, or chapter 7 was already due, and all that stuff. So I just finished changing all those. So just for the record,
Okay, thank
let
you.
me let you know what they are now. Chapter 7 is now due on the 17th, conceptual and homework. So that's this coming Sunday. I've made chapter 8 concepts due 3/17, so it's the Wednesday after Sunday. And 3/19, no, 3/17 is the same as the Sunday. Sorry about that. And then the homework for chapter 8 is due on 3/19, which is the Wednesday. And then I pushed chapter 9 back to the 24th. So hopefully that helps everyone. I'm
Sounds
sorry about
good.
that. Sorry if I gave everybody a heart attack for having to do a homework assignment before we even finished the chapter. So I don't know.
I did have a little bit of a heart attack.
Yeah, I got one text message from someone and I didn't find it till late, and then I completely forgot about it the next morning. So I ended up not replying. And then this morning I remembered it. I felt so bad. So hopefully it wasn't you. If it was, I apologize. Or whoever it was, I apologize either way. So I've now got 7, 8, and 9 set up with the proper dates. Okay, so yeah, Hannah, you were taking at a distance. So you need, if you're actually, you're supposed to take it to the exam room, or excuse me, in the lab room with your lab instructor. Some students had to drive a really long way, so I allowed them the ability to take it with the lockdown browser and the monitor, as well as you have to have a mirror behind you so that I can see basically your screen as well as everything else. But if you want to qualify that way, then you just need to make sure you have Respondus lockdown browser, Respondus monitor, a camera, webcam, obviously, or else the Respondus monitor doesn't work very well. And I need a decent sized mirror back here where I can see from that camera, see basically what's going on with your hands and or with the screen. So that's the main thing. Uh, I can't remember. Hannah, were you the one that was driving from the Eastern Shore, or I don't think that was you. I think it was, I know Logan did. I think that's who I'm thinking of. All right. Yeah. All right, so let's get started into chapter 7. We last talked, I sort of made some heuristic arguments about how the work relates to work, the common word that we use. And I think I made a pretty good argument to suggest it's reasonable to expect that the work done is proportional to the force, that the work done is proportional to the distance over which you apply that force, and that it also in some way relates to how that force is either parallel, anti-parallel, perpendicular, that sort of thing to that displacement. And then in the event that it actually is a varying force, either in magnitude, direction, or both, I've showed a way to combat that as well. So I'm going to go ahead and share my screen. And evidently it's going to make me download something again, as it always does about once a week. Okay, so that should work now. All right, I've got the iPad transitioning to sharing with you guys, and I'll put the ultimate equation down. There you go. So what we were able to put together last time was that the work is directly proportional to the force, the work is directly proportional to the displacement, and hold on a second. I gotta put up my chat window too. Okay, there it is. And that it's also related to how parallel the force was to the displacement. And in fact, I showed you that if we had a simple situation where the force was parallel to the actual displacement, then work is equal to force times displacement. But if it in fact made an angle with the displacement, then the force would be F times D times the cosine of the angle between them, where we're going on the assumption that F would be a constant force like shown, and D, the displacement vector, would be a constant displacement. And when we put them tail to tail, the angle between them would be theta, so that you could make some sense of why the cosine theta is there. So hopefully that makes some sense. And then if we allowed for the possibility of you, as you change your position on space, you might actually change the magnitude and direction of the force and the displacement vector. So you could actually, in principle, have a position versus time graph that looks something like this, where you're basically doing something like this. Okay. If that's the case, then what we need you to be able to do is imagine this little DL vector right there. And hopefully you've narrowed that uh, width of that DL so narrow that the force doesn't change appreciably over it. And then you can do just F times DL times the cosine of theta, where you're just using the magnitudes for that particular part. And then you do the same thing for another part and the same thing for another part and so on and so forth. If you divide it up small enough, then the force won't change particularly badly, and you can just add up the individual pieces. In principle, you can see that you can generalize this to allow the DLs to be infinitesimally wide, in which case you make it a Riemann sum, and the work becomes the integral of F dotted with DL. And as I told you, your book and me are letting you know that this is a path or line integral. Okay, so what that means is, actually, let me fix this. What that means is you have to actually take the integrand and set it up so that the integral is being carried out over an integrand that's evaluated on the actual path. So, for instance, in general, f could be equal to f sub x, which means the x component of f, which could be a function of x, y, and z, I hat, plus f sub y, which again could be a function of x, y, and z, j hat, plus f sub z, which again is a function of x, y, and z, k hat, and dl in general would be dx I hat plus dy j hat plus dz z k hat. And if you find this in your calculus book, there it will be there. You'll find a path integral or a line integral. You'll find surface integral, stuff like that. But you'll find they do it quite a bit differently from the way we do it. Like when we deal with vectors, we deal with an x component, a y component, and a z component. A lot of times in vector calculus for a mathematics department, they would express a vector as a coordinate plus some number t times another coordinate. And in so doing, they have a parameter t, and it's a parametric equation. And then they have a parametric equation for the path over which you integrate. So it's carried out a little differently. Whereas, like, if we were integrating along the path y equals x squared, then that would mean dy is equal to 2x dx. And if you had, for instance, f was equal to, let's say, y plus x squared I hat, something like that, then what you would do is to evaluate it on the path, you would replace y with x squared. So you'd say x squared plus x squared times I hat, which is I'm just making up a nonsensical one, but the main thing is so you have some idea. Now you'd have a 2x squared I hat would be your force vector, and your DL vector might in fact be dx I hat plus 2x dx j hat. So that's some of the stuff you would actually do in an everyday physics type class when you're computing a line integral or a path integral. That gives you some idea of how you're going to do it. And most of the time, it really doesn't matter too terribly much because you can do it almost ignorantly and often get the right answer. So, meaning, and I don't mean ignorantly trying to insult anyone. I just mean not even knowing that it's a line integral as opposed to just a regular interval. I've seen people get the right answer repeatedly. Okay, so it's a big safety factor here where you oftentimes can get away with it. But I'm trying to teach good from bad, and the good is that this is a line integral, and you need to do certain things to make sure you do it right. So one of the things when you're doing it this way that you want to do is you have to let your direction of integration be given by the direction of dl or by the direction of the limits of integration. Okay. But I'll say not both. Okay. So what I mean by that is, well, let's take a specific example. So there happens to be a force called Hooke's law. And Hooke's law doesn't just apply to springs. However, that's what we always use it for, almost all the time, use it for in physics. And what Hooke's law says is that the force that a spring applies, F sub S, is equal to a negative times the spring constant, which for a spring is called the spring constant. But in general, Hooke's law applies to any solid object. If you actually put a force F on a iron rod, and that force is such a force that would tend to stretch the iron rod, then the iron rod will actually elongate by a small amount x, such that the force times is equal to K times that X. Now, the problem is when you're dealing with solid objects like a solid iron rod or even, balsa wood, it takes a huge amount of force to stretch it, or if you go the other way, if you compress it, it's also going to shrink by an amount. It takes a huge amount of force to actually see that a measurable change in length. So by using springs, we can easily see the measurable change in length. And that's why we tend to use Hooke's law with springs as opposed to the other end, because it's actually dangerous to, apply huge forces to, iron rods and stuff like that, because they literally could break under compression. Shards could fly off over the place, stuff like that. So in general, what we do is we say Hooke's law is F is proportional to the uh, either the stretching or the compressing of the actual length of the object, which we're going to say that stretch or that compression is given by X. And then this negative sign just indicates that, hey, if you have a spring and you're pushing, like the spring is parallel to the x-axis with the equilibrium position of the spring at the origin, and if you were to stretch it, you would go from x equals 0 to x equals something positive, and if you compressed it, you go from x equals 0 to x equals something negative. So if I actually push in the negative direction, the spring's going to push back on me in the positive direction. That's what that negative is for. Okay, so force is in opposite direction of X. In other words, if I go from X equals 0 to X equals -1 centimeters, I'm clearly going in the negative direction. And the force the spring is going to apply to me when I push it that way is in the positive direction because of that negative sign. Okay. So this is called Hooke's law. And this quantity right here is called the spring constant. If you're dealing with everyday objects like a 2x4 or something like that, there's something called a modulus of elasticity that can be used. But in case of the springs, we just use a spring constant, and it'll have units of like newtons per meter. So let me draw a coordinate system, and then we'll use it to actually calculate a work. And that'll give you an example of what I mean when I tell you that weird stuff by choosing the direction of integration to indicate by the DL or by the limits of integration, blah, blah, blah. That's not the easiest way to think about it. So what I'm going to do is I'm going to draw a X and Y coordinate system right here. I am going to draw a spring system, which is going to be against this wall right here, and then right here. So this is like a surface, and in fact, there's going to be a spring right here, and I'll say x equals 0 implies equilibrium. Okay. So if I were to apply a force until the spring becomes something like this, then the actual amount of stretch that has occurred is from here to here. Okay. Now, what I want to do is calculate the work done in stretching the spring, but I'm going to do it in such a way that I just barely apply the amount of force that's necessary to stretch it. I don't want to give it so much force that the actual end of the spring actually maintains or even approaches a measurable velocity. Because if I did that, I'm actually introducing a new kind of energy that we haven't figured out how to deal with yet. So in order to do that, I have to actually let the magnitude of my force be exactly equal to kx. So I'm going to say, in this case, the work is equal to the integral of f dot dl like this. And in this case, since I'm stretching it to the right, I can clearly see that the force I used, F, is equal to a positive kx I hat. Okay. So I'm going to put k times x times I hat is the direction of the force I'm applying. Actually, is the direction of the force I'm applying. Now, here's the case where I either use the limits of integration to indicate that I'm integrating to the right, okay, or I use the DL to indicate that I'm integrating to the right. In this case, I'm going to choose the DL to indicate that. So I'm going to say DL is actually equal to positive DX I hat. Okay. So indicates direction of integration. Okay. Now, because of that, I have to just choose my other method of indicating the direction. I need to choose that to be in the positive coordinate direction. So the k is a constant. That's going to come out in front. The two plus symbols are positive. That's going to come out in front, and they're constants, that sort of thing. So all I'm left with now is the integral of x dx times I hat dot I hat. That's what's actually going on with the integral. And of course, we know that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So in this case, it's going to give me 1 times 1 times the cosine of 0 degrees, which is in fact 1. Now, I have to integrate from x equals 0, which is the smallest value, to x equals x, which is the largest value. So I'm saying this is x. So notice in this case, the integration, the limits go from small x to larger x. So that's what I have to do with the limits of integration, since I chose to show the direction of integration by using my direction of DL. In this case, you can see they both did the same thing, right? I happen to be integrating in the positive direction, so my DL was positive DX I hat, and then I had to put the other thing in a positive coordinate direction, which is from x equals 0 to x. So it's the same way. So had I done both of them, which is not appropriate to do, I still would have got the right answer. Okay, that's what I meant by when I was saying that you can do it ignorantly and still get it correct. Okay, there's a lot of room for error in here, but the one time that you really, really need to succeed will be the one time that you don't do it right. So that's why I'm stressing this, to show you exactly what happens. Now, I can do this. The integral of x dx is the integral of x to the 1 power. The integral of x to the 1 power is x to the 2 power divided by 2. So ultimately, my answer is going to be, not in red, but in blue, is going to be 1/2 k x squared. And then I've got to evaluate that from 0 to x, which gives me 1/2 k x squared. So that's the actual work done in stretching the spring from equilibrium, x equals 0, to x, which is not equilibrium. Okay. Any questions on that? Now let's look at an alternate way. Let's say it's the integral of kx I hat. This time, I'm not going to do it. In this case, it literally would just be the exact same thing. I would much rather have a time where I'm going to draw the whole diagram over and go in an entirely different direction. So if I tried to do it again with the same direction, I'd get the exact same integral, but I would basically pretend like I'm indicating the direction with x equals 0 to x equals x, and then I just put the dl and the positive dx I hat. So you see, you get the same response. I will tell you this though. We're going into chapter 8 after this. We're finishing chapter 7 right now, and the whole thing that we're dealing with in chapter 7 and 8 is the concepts of work and energy. Uh, I tend to define energy as the ability to do work, and then I define work as anything that can drive a nail. Only I've got to put some caveats on that because you might think to yourself, well, there's no way in heck that any kind of atom, for instance, can be used to drive a nail. And in some sense, you're right. You know, any nail you can think of, I cannot think of a atom moving in such a way that it could actually drive the nail uh, in any easy way. So it might seem unreasonable to say that an atom could drive a nail, but an atom can, because you need this extra caveat. So I say energy is the ability to do work. So if something has energy, then it has the ability to do work. And then I also say that work is anything that can drive a nail. And the caveats I use is that the nail can be as small and sharp as necessary, and the material that you're nailing it into can be as soft as necessary, even down to the point of being like hot butter. So you could imagine a nail that is literally one atom in diameter, maybe 10 atoms long, and it goes from an atom to nothing. So it's sort of blunt ended in that sense, but the end is so small that it can pretty much go through anything because the atoms are about an atom apart. So you can just force the atom diameter nail into a hole between two atoms, and by applying that force over the distance that is the length of the nail, you get a certain amount of work being done. So that's how I tie those two together. Then I start thinking in terms of what kinds of energy are there. There is the energy that has the potential to do work. That's one way we use it, but I also call it the energy of position. Okay. And it's called a potential energy. And then there's the energy of motion, which we call the kinetic energy. So, what we want to think about as energy is the ability to do work, and it comes in a lot of different varieties. So, there's the energy of position that, for instance, could be the energy that the planet Mercury has as a result of being, you know, zero point 0.4 astronomical units away from the sun. And the sun, of course, having a gravitational pull, has a certain amount of pull on it. And therefore, if you were to not, or if you were to stop Mercury from orbiting, in other words, stop its velocity, then Mercury would perilously fall towards the center of the sun. And what's going on there is it's at a high potential energy because the gravity of the sun is pulling Mercury towards it. And as soon as you don't have enough velocity to keep it from getting closer as it falls towards the center, then it's going to actually fall towards the center without any hindrance. And that's going to lead to it speeding up. And then it's going to go further and speed up more. And then, in fact, once you get to the place where the center of the sun would be, if you could magically move the sun out of the way so that it didn't interfere, what you would find out is right as it got to the center of where the sun is, the planet Mercury would have exactly the same kinetic energy. That's that energy of motion I told you about, as it did potential energy when it was out of its orbit. So that's where the conservation law comes into play.
So, I just have a quick question
Yes.
about like the way you define work.
Mhm.
So, can I just so I'm trying to get it if I'm getting it right. So you want anything that could move anything else, no matter how small, like the distance that it moves something, will be
Yeah.
considered work. Okay,
Yeah. So we use it in terms of thinking about this same formula, work equals integral of F dot dl. So you think about a force applied over some distance. That's how you do the calculation. And that's what makes it the work. So long as you've got anything that can apply a force over some distance, that's going to be doing work. That's why I use the nail as opposed to just, anything that can make a ball speed up, you know.
gotcha.
Does that make sense?
Yep, that makes sense.
Okay. All right, so we now have a formula for the work done in stretching a spring. And what you're going to find out is that if I actually did that work to the spring, now the spring has a potential energy, U for the spring will equal 1/2 kx squared. Because that's sort of the way we want energy and work to work together. If I put a certain amount of work into a system like I did just now by stretching the spring from x equals 0 to x equals x, then I expect that energy to have not just disappeared. And in fact, what I do is say, well, it's not moving. So I'm going to call this an energy of position. And an energy of position is a potential energy. So I'm going to just set that work that I did equal to the potential energy. That's going to be a theme over and over again. For instance, if I take a mass M and I apply a force upward, mg, then that force is just enough to keep gravity from pulling it down. Now, if I just apply an infinitesimal amount above that mg, then it will actually move up ever so slightly. But since it's an infinitesimal amount, it really won't be moving in the sense that you could measure a velocity, but in the sense that it's going from x equals 0 to x equals 0.000000001. Yeah, it's moving, right? And you keep doing that until you're all the way up to x equals x. At that point, you've managed to move it from x equals 0 to x equals x without increasing its kinetic energy. Therefore, you converted all the work into something called potential energy or energy of position. And that's what we're going to use to calculate potential energy in general. We're going to try to calculate the work done in moving an object, say, from ground height to some height h, and make sure we do it so slow with such a small force that it doesn't gain any kinetic energy. And when we do that, we can say the work is equal to the change in kinetic energy. So in addition to us treating the work done in stretching a spring as 1/2 kx squared, we can also think that when a spring has been stretched a distance x, or when a spring has been compressed a distance x, it will have a potential energy given by 1/2 kx squared. Does that make sense to everyone? All right, so let me show you another example and then we'll maybe investigate the spring again. So let's imagine, for instance, we have a mass right here, a mass M, sitting on the ground, and we wish to lift it up to a distance right here, okay? And that distance is going to be 8. I would like to know the work done in lifting it. So again, I'm going to say work is equal to the integral of F dot dl, and I'm going to let the force be just big enough. So the force, let's do it this way. Let's say F is equal to F min, which means the minimum force required to actually lift it. So in this case, I'm going to say F min is M times G in the downward direction well, actually, since I'm talking about the force I'm applying to it, it's going to be in the positive direction. But the main thing is it's going to be in the J hat direction. Okay. And then I'm going to say my DL. This time I will just point it in the positive coordinate direction. So I'm going to say my DL is DY J hat like that. And then I'm going to integrate and use that to indicate which direction I'm going. So I'm going to integrate from y equals 0 to y equals h. Okay. Now notice this is in positive coordinate direction. So it's doing everything right. But again, we're in that same scenario like we just did. Notice I am using the bare minimum. So it's supposed to be like a infinitesimal amount bigger than mg. So we're just going to call it mg. And I'm going to say the force is m times g. I'm going to use the right color. M times g times j hat dotted with dy j hat, which gives me m times g, all being constants from y equals 0 to 8 of dy, and then j hat dot j hat, which is 1. So I end up getting m times g times h like that. So in general, that means delta U is equal to the work done, which equals mg times parentheses h minus 0. So now you can look at delta U as U final minus U initial, which is mgh minus m times g times 0. So we have a new energy source, and this one's called potential energy. So that's a new type of energy that we hadn't talked about. We hadn't even really talked about energy yet. We'll do that more in the next chapter, but that's where we're going with this. And as I said, this is also called energy of position. Now, that's only applicable where the forces of gravity are about equal to m times g. You know that once you get a distance away from the center of the Earth that's, comparable to 2 or 3 times the radius of the Earth, then the force is more like m over r squared. So there's a whole different process for going about finding out that potential energy. But if we're within, let's say on the order of a half of a Earth radius or smaller, then it's probably okay to use mgh for the potential energy. Now let's do again. This time I'm going to do the spring, but I'm going to do the spring in a way that hopefully is a little bit more instructional with regards to the rules of line integrals. So let's say this is my wall here, and that's my floor. And I've got, in fact, a spring attached to the wall. Like that. Okay. Actually, let's go a little further. Let's say this is X equilibrium. Okay, that little position right there is supposed to be X equilibrium. What I'm going to do is apply a force F this way. And I'm going to push it all the way to, let's say right here, x1. Okay. And now I want to calculate the work done. So what I'm going to do is I'm going to say work is equal to the integral of f dot dl. In this case, I'm going to again apply the principle where only the bare minimum work is being done. So the quantity or the magnitude of the force is just going to be k times x for each x, but it does point in the negative direction. So I'm going to say negative k x and an I hat. Oops, I wrote a j hat by mistake. And an I hat with that. That's the actual force. And now I'm going to let the DL indicate which direction I'm integrating. And you can see I'm integrating in the negative direction. So I'm going to say it's from, it's a negative dx I hat like that. So this one indicates direction of integration. Okay. And now I have to just integrate from small x value to large x value. So I'm going to actually integrate from x1 to x equivalent. Okay. So now when I do this, it's going to become a negative times a negative is just a positive. So I'll put a positive and a k out front. And I'm going to do the integral from x1 to x equivalent. And of course, this is just going to be x dx times I hat dot I hat, which of course is 1 again. And this time it gives me 1/2 k x squared from x1 to x equivalent. So it's going to be 1/2 k times x equivalent squared minus x1 squared like that. But remember, x equivalent basically gives you an energy equal to 0. So I can write this as 1/2 k x equivalent squared minus 1/2 k x1 squared. But this by necessity is equal to 0. Okay. So that's what I mean by showing your limits of integration versus using your DL to indicate the direction. Anybody have any questions on that? All right. So now that we have that, we're going to do another example, and this is one where your book is actually doing something like it. Basically, your book says yes.
Excuse me,
Yes.
could you just go back real quick 1 second so I can take a picture of that?
Yeah, no problem.
Sorry. I was trying to write it all, but. Got it. Thank you.
You're welcome. I was just trying to make some sense out of having a negative amount of work. I don't want to scratch that too much, so I'll leave that be. All right, there's a problem in your book where they make up a rather idealized problem for a variable force. Specifically, they take a mechanical device and they say the force of this mechanical device when the object is at a position X is actually equal to F0 times 1 plus x squared over 1 or times 1/6 over x0 squared. And they do so such that F0 is equal to 2.0 newtons. And I'm trying to remember the other numbers. Yes, is 2.0 newtons. X0 is equal to 0.0070 meters. And we're going to, in fact, take it from x1, which is 0.010 meters, to x2, which equals 0.050 meters. So what they want to know is how much work is done. So I'll say solution. And the solution is going to be work is equal to the integral of F dot dl. In this case, notice it's a one-dimensional force. One-dimensional force means the force is only acting along a parallel to the x-axis or anti-parallel maybe to the x-axis, and the dl is only going to be along the x-axis, so there's no real need for a dot product or any of that kind of stuff. But there is a need for a integral because the force is a function of position. So what I'll do is I'll just say it's the integral of f of x dx like that. And this is going to become f0, which is a constant, times the integral of 1 plus 1. Make sure it's 1/6. Yes, 1/6 x squared over x0 squared times dx. And now I'm integrating from x1 to x2. So when I go to integrate this, what I'll end up getting is f0 times, now what's going to happen is I take the integral of dx times 1, that's just going to be x, and then I take the integral of x squared times 1/6 and divided by x0 squared, and that's going to become the integral of x squared becomes x cubed divided by 3. So this is going to become 1 over 18 because 6 times 3 is 18. And it's going to say x cubed over x0 squared like that. So now I can put in 2.0 newtons times. Now I'm evaluating this at x1 and x2. So what I'm going to do is put in the x2 first, which is 0.050 plus 1/18, 0.050 meters cubed over 0.0070 meters squared. And then I'll put a curly bracket around here so I can separate those. And I'll say minus square bracket 0.010 meters plus 1/18 of 0.010 meters cubed over 0.0070 meters. This is all going to be squared, and then like that. So now I can go about computing this, and I'm going to say it's 2.0 newtons times, now I'm going to say 0.05 plus, I'm going to do 0.050 cubed, and then I'm going to divide that by parentheses 18 times 0.007 squared, close parentheses, And that looks like it's right. So this figure right here is just going to become 0.1917 Newton meters. And then this quantity inside this bracket is going to be 0.01 cubed. I'm going to divide that by parentheses 18 times 0.007 squared, close parentheses. And now I'm going to add that to 0.01. And that gives me 0.01113. And actually, neither one of these are Newton meters. These are just plain meters. Sorry about that. I forgot I hadn't multiplied the 2.0 in there yet. Ah, darn it. So this is just a meter right here. Everybody follow what I did there? 0.01. Looks like I typed it in correctly. 0.01 cubed over 18 times 0.007 squared. Got that. Added 0.01 to it. That gave me that. That looks good. Okay, so now I'm going to take the 0.1917 meters minus the 0.01113 meters. And it looks like I forgot to erase the right unit here. And point 19172, carrying one extra digit, minus 0.01113 gives me 0.18059 meters times 2 gives me 0.36118 Newton meters is what I got. Now, I don't remember that being the actual figure. Nope, that is the actual figure. Okay, so I did get it right. Anybody have any questions on that one? Now, if you dig a little deeper in that, you look and see you have a 0.050 cubed divided by 18 times 0.007 squared, close parentheses. That basically gives 2 sig figs, and those sig figs are in the tenths place and the hundreds place. And then when you add that to 0.050, that actually still only gives you 2 sig figs. And they're both the tenths and the hundreds place. When I do the other one, 0.01 cubed, and then I divide that by parentheses 18 times 0.007 squared. Now that one gives me 2 sig figs would be the hundreds place and the thousandths place, which is pretty small. And then I add 0.01 to that. And that actually gives me to the hundreds place and the thousands place is all that I get. So when I subtract, and actually everything to the left of it has to do this, so thousands place, tenths, hundreds, thousandths. So basically this digit and this digit are not sig figs. but I do get 3 sig figs out of it, so that should give me 0.361 is roughly where the right sig figs are. Sorry about doing all that side calculation. I just want to keep you guys up to speed with the appropriate number of sig figs and all this stuff. Anybody have any questions on that problem? So this was like example 7.6. So I'll write it up here just so you guys can keep track. Now I'm actually looking at an old edition. Hopefully they didn't change the example number or didn't completely axe it. Either way, I've given you a problem that you can solve. So even if they did get rid of it, at least you know how to work it, that sort of thing. One of the things that I want you to realize is by saying the work is equal to the integral of f dot dl, that forces us to, if we actually make a plot of force versus distance, force on the vertical axis and distance on the horizontal axis, then by necessity, the area under the curve will be the actual work. So I just want to remind you guys of that. Area under f of x versus x curve is the work done. Okay. All right. So that is essentially all the sort of examples that I think is necessary for you to have experience with doing work integrals and stuff like that. When we actually get into the second semester, the 242 course, we'll do a lot more of these line and path integrals. And in that case, there will be more opportunities for you to do it in such a way that if you make a mistake, you'll actually get it wrong. Whereas a lot of the ones that we do in the 241 class, it's really hard to make a mistake, just because often you're integrating in the positive direction and you're integrating from a small number to a bigger number, in which case the two DLs and the limits of integration are the same. So that's why it really doesn't matter too much. But I wanted to show you some of that. What we have to go on to now is something called the work energy theorem. So let's start off with that. This is called the work energy theorem. So what I want you to do is start off with Newton's second law. So Newton's second law is that the net external force acting on a system is equal to the mass of that system times the acceleration. But I'm going to use dv dt instead of a because that allows for the differential equation, because the a being over there only applies when the total force is a constant. If the total force is not a constant, then the well, unless the m has some weird variable expression, there's no way to make the a constant, so you have to use dv dt. Now what I'd like to do is I'm going to take this and dot each side with a dl. Okay, and I'm going to dot it on the left. And in so doing, I'm also going to integrate, and what I get is the integral of the summation of the forces dotted with dl is in fact equal to the integral of m dv dt dotted with dl. Now I'm going to be kind of ingenious and replace or exchange the dv and the dl's position to get the total work, which is equal to the integral of the sum of all the forces dotted with dl, is equal to the integral, there we go again, is equal to the integral of m dl dt dotted with dv. Well, you probably recognize that dl dt is the same thing as v, in which case we get equals, actually, let me go ahead and stick to purple, equals integral of mv dotted with dv. So the integral of mv dv, I think you can figure out, is 1/2 mv squared. So what we get is work net, that's another version of it, or work total. And what I mean by that is you take all the forces acting on the system, and each one gets a F dot DL applied to it. And then we're going to sum up all those works from all those different forces, and that'll be the total work. But it's going to come out to be 1/2 mv squared from V initial to V final. So what we say is work net, which equals work total, which equals delta K like that, where K is defined to be 1/2 mv squared. That's the work energy theorem right there. And it basically says, hey, no matter what, if you add up all the work done on a system in any period, then that total work done, God, I'm sorry, then that total work done will equal the change in kinetic energy. The total work done will always be equal to the change in kinetic energy. So this often is used, for instance, by police officers. If you have a car accident that you're on the scene of and you want to ascertain exactly how fast, say, one of the drivers were going, you can actually look at their skid mark, because the skid mark is an indication of when they started skidding. And skidding means that their tires have basically been stopped from rotating. And because they're not rotating, they're skidding across the actual road surface a certain distance, acting against the force of friction. That friction force, which is normally mu static times the normal force, is a constant force. And if you integrate a constant force that happens to be opposite in direction to the displacement, then you just get a negative force times distance. So that would be what the left-hand side is. So in the event of a car accident, for instance, you would have on the left-hand side a negative due to the cosine of 180. You would have mu kinetic due to the skidding, the coefficient of friction between the tires and the road surface. The normal force, which if the car is on a horizontal surface, the normal force should just be m times g, unless there's some other weird forces acting on it. And then all of that times the distance that the skid mark left. In other words, if the skid mark was 20 meters, then d would be 20 meters. Well, all that is the work done by friction, and then that has to be equal to 1/2 mv final squared minus 1/2 mv initial squared. If you go on the assumption that they reached a stop at the end of the skid mark, then you end up getting negative mu k mgd is equal to negative 1/2 mv initial squared. You can see that the masses, in fact, cancel out, which is good because that means skid mark's sort of independent of what kind of vehicle you're driving. And ultimately, what it tells you is that D is directly proportional to the square of the initial velocity. So if a car at 20 kilometers per hour requires 12.0 meters to stop, whoa, wrong word. How many meters are required at 60 kilometers per hour? Can anybody answer that question for me? Anyone? Giving you a couple seconds to try to work this out or think about it.
Would that mean you'd have to take the square root of 60 since your initial velocity square would be 60?
Very, very close. Okay.
Okay.
So what do you have to multiply by 20 to get 60?
3.
3. So if I multiply the velocity by 3, what happens to 3 squared? Or what happens to the
It
velocity
doubled.
squared?
Or
You're on the right track. It's
that
just a weird word.
So it becomes 180?
There you go. Because you're multiplying by 9, right?
Mm-hmm.
Yeah. So basically, yeah, you're right. Because the d is proportional to the square of the velocity, if you increase the velocity by a factor of 2, you're actually increasing the velocity squared by a factor of 9, which means you're going to have to increase the distance by a factor of 9. 9 times 12, well, 9 times 10 is 90, and then 9 times 2 is 18. So it'd be 90 plus 18, which would be 108. I know what you said, but I also understood what was going on. So in fact, the D would be equal to 108.0 meters, which is 9 times 12.0 meters. That's the key rule that we're trying to learn by that problem I wrote where I said car accident and I said D is directly proportional to V squared. Okay. That's why these speed limits are very important. That's why a 35 mile per hour school zone is a very important thing. If you're actually driving 35, maybe it takes you 4 meters to come to a stop. If you're driving at 70, which is twice as fast, then instead of it taking 4 meters for you to stop, it's going to take basically, since we went from 35 to 70, that's a factor of 2. It's going to take 2 squared, which is 4 times as much. So instead of 4 meters, it's going to take you 16 meters to come to a stop. Okay. Now, that's one of the many uses of the work energy theorem, but just keep in mind, with the work energy theorem, we've introduced a concept of kinetic energy. This is the energy of motion. So kinetic energy. All of them, of course, have units of joules. But this is the energy of motion, whereas the potential energy is the energy of position. Does that make sense to everybody? All right, so we are now officially, quote unquote, done with chapter 7. Let me see if there's any specific examples I'd like to work for you. I think I'd like to find a example of a path integral and do that for you. Let's see. I don't see any other ones jumping out at me as something.
So for the concept question,
Mhm.
um, so you plug in the first two like kind of values for the speed and the 12 meters. You plug that in, you find the UK, and then you plug the UK in and you get the distance for the 60 kilometers per hour.
That is the brute force method that would work. What I was trying to get you to do is to use the concept. So when I say use the concepts, there's certain expressions that lend themselves to quick analysis. Let me show you what I mean by that. So if we say, for instance, y is equal to k times x, what we see is y is on the left and it's on the top. And what I mean by that, I mean that I can write it as a fraction with 1 in the denominator. Okay, so it's in the numerator. And then we also see that the variable x is on the right of the equal sign. So I'll say actually, of equals. And I'll say of equals. But I could also put a 1 under there like I did with the other side, and I'd see that it's also on the top. Okay. And I'd say of fraction. Of fraction. Any two type of variables like that are what we call, here's my drawing of a fist. Thumbs up. Thumbs up. And what that means is if x goes up by a factor of 2, then y goes up by a factor of 2. If x goes down by a factor of 1.7, then y goes down by a factor of 1.7. You can try this yourself just by plugging in for two particular values and then keeping that solving for k and then keeping that k. And what you'll see is if you put in x equals 2, you get one answer for y. Then if you put in x equals 4, you'll get twice as big an answer for y. If you put in x equals 9, you'll get 9 times as big an answer. So that's one of the rules. Thumbs up just means that when one goes up, the other one goes up. And the fact that they have no exponents means that the 2 stays a 2 from left to right on those arrows. Now, if I do this and say, let's say d is equal to some constant times x squared, what we see is d is on the left and top, and we see that x is on the right and top. So they're thumbs up too. But if x goes up by a factor of 3, then d goes up by a factor of 3 squared, which means d goes up by a factor of 9. If x goes down by a factor of 2, then d is going to go down by a factor of 2 squared equals 4. Let me show you one more. Let's say y is equal to k over x cubed. Not because that's a particular example that's that helpful, but because it gives you another data point. So what I see here is y is on the left and it's on the top. But what I see here is X is on the right, which is good, but it's on the bottom. When that happens, what we get is thumbs up, thumbs down. See, when one's in the numerator and the other one's in the denominator, then they're thumbs up, thumbs down. And what that means is if X goes up by a factor of 2, then Y goes down by a factor of 2 cubed, which is 8. If X goes down by a factor of 7, then Y goes up by a factor of 7 cubed, which is a really big number. 7 times 7 is 49. 7 times 40 is 280. 7 times 9 is 63. That's 343. Something like that. So that's what I mean when I try to get you to do this. D is proportional to VI squared. You see the D's on the left of an equality or a proportional symbol, and D is on the top. You see the initial velocity is on the right side of the equals or the proportionality, but it's on the top as well. So they're thumbs up, thumbs up. And then it's just a matter of accounting for the exponent. And the way you account for the exponent is as I did here, where if you double the variable, then you don't double the other one, you double the other one squared, which is 4 times. Does that help you?
Yeah, I think so.
I know it's a lot more stuff than you wanted the answer to, but you can completely what you said. You could completely take 2 answers and compute, all the stuff about the mu and the g and all that and get a d, and then plug in a new velocity. Instead of it being 20 kilometers per hour, you could plug in 60 kilometers per hour and you'd still get 108. That would be fine. It's just that takes a lot of time. So what we want you to understand is when we look at an equation, what does the equation mean? So if you have a y equals some number times x squared, that should tell you, oh, it's thumbs up, but it should also tell you that it's thumbs up with the x variable being squared, so that if I double the x, I quadruple the y, or if I triple the x, I 9-tuple the y, or if I quadruple the x, I 16-tuple the y. So I'm just trying to give you a quicker way of doing that. I didn't really
So,
see. Go ahead.
so basically what it is, since the distance goes, or the velocity goes up by a factor of 3, then the distance would go up by a factor of 3 squared.
Exactly.
Okay.
Yeah, because I went from 20 to 60. So if you did 60 divided by 20, you get 3. And of course, 3 squared is 9. So that's where that came from. Does that make sense, Caden?
Yes, I think I understand it.
Yeah, so we spend a lot of time doing that kind of stuff, like in the conceptual physics, which is kind of a shame because that kind of stuff really gets you a feel for how the equations work. And it's, that's one thing that could help you a lot in studying physics, but we just don't have the time because we've got to show you how to solve problems and stuff like that. But that's a pretty good intro, I think, to chapter 7. Next time we meet, we'll do chapter 8. And sometimes I actually completely finish chapter 8 in a single setting because I've done a lot of stuff already that points to what chapter 8 is. And I have a different version of the equation that your book uses. I use a slightly different version. And it's just a matter of me showing you a couple examples with those various versions. Okay. So we are done. You've got like 1 minute left before class starts, or before class is over. So that's close enough to me. And you guys are free to go. I'll wait for the last person to split in case anybody has any questions, but you're free to go. Thank you for coming. Good luck on your exams on Thursday.
Hey, Professor Younger.
Yes.
The exam is everything from chapter 1 to 7, right? Not just 3 to 7, right?
That's correct. And it's only part of chapter 7. I think I put pretty much up to just calculating work.
Okay.
So it
Do
shouldn't
you?
be terribly hard.
I know you're doing like the Zoom office hour thing, but do you also have like just in office hours or no?
Yes.
Guys, it's
Wednesday I'll be in at 8 a.m. at 8 a.m. And I have that office hour from 8 to 9. And then I have another one usually by around 10:30. You can see me in my lab or in my office. And then I have another one at 1:20.
120.
Mm-hmm.
Okay. All right. Thank you.
And that's on Wednesday. All right. See ya. Caden came back.
Yeah, I just remembered on that one extra credit where it was like about the Earth and the moon, and then the other question was like a basketball and
Ah,
other
right. Yeah.
stuff like that. It was asking for the dimensions
Mm-hmm.
about the divots or whatever and
Mm-hmm.
the pimples of it, and I couldn't find anything about like those dimensions on it. So I had submitted like a picture of my work, and I just wrote down on there like couldn't find any dimensions for the basketball like that.
Okay. What I would tell you to do is that the pimple on the basketball is about a millimeter tall,
Okay.
and the groove is about a millimeter deep. Then you just need the radius of a basketball, which I suspect that one's probably easy to find.
Yeah.
So if
Okay,
you
thank
want to
you.
use that, you can get a more fuller credit. And if you turn it in before I grade, I'll give you the full credit on it.
All right. All right,
Okay.
thank you.
So you can think of the change as being just a full 2 millimeters, and
Mm-hmm.
then figure out I think I found that the circumference is 26.5 inches. So you could actually divide that by 2 pi, and that should give you the actual diameter. Or excuse me, divide it by pi, and that should give you the diameter, or divide it by 2 pi, and that should give you the radius. But I think that's what I discovered. Let's see. Radius of basketball. Ah, no, it's actually saying they're saying the diameter is 29.5 inches. I thought that was the
Oh,
circumference. It don't feel like that big, does it?
no.
Ah, there you go. Standard NBA basketball has a diameter of 9.43 to 9.51 inches. Ah, they did. Okay, I just saw now. I barely read the writing on here. It said 29.5, but it had it drawn this way. But then
Hmm.
under it, there's a little white blur, and that said circumference. So circumference was right. So the actual dimension is 9.43 to 9.51 inches in diameter,
Okay.
and that's for NCAA and NBA.
Cool, cool. All
Oh,
right. Thank you.
all right, no problem. Have a good one.
Thanks, you too.
Kayla, do you have a question, ma'am?
Yes, hello. How are
Hello, how you
you?
doing? All right.
Good. I had no intention of missing lab today. I had an emergency come up,
Well, I hope
and if
you're
I had
okay.
oh yeah, I am. It's been an interesting day. So I was trying to go ahead and pop up here, but had I planned for all of that to occur, I would have let you know in advance.
No problem.
But I'm trying to figure out the best path for me to go ahead and if I'm able to make up a lab or just what I need to do.
Uh, where the problem is my Monday lab is 1 week behind, so everybody's
Yeah.
already done the lab.
Okay.
That being said, uh, they don't change it over till tomorrow. Yeah, I don't think there's any way you can do it. Yeah, have you missed another lab before?
No.
Then I wouldn't worry about it. I actually dropped your lowest lab grade, and if you miss a lab, I give you a 99 out of 100 for attendance. If you miss two,
Okay.
it comes a 95. So 1 point's not going to hurt you. And usually I even give that 1 point back. So
Okay. All right. Well, I don't have a plan on missing another lab anyway, so
well, you better not.
yeah. All right. Have a good one.
All right, you too, Kayla. Have a good day.